let's use this slide and talk about how to fill out these different types of reactions, or these different types of equations for a given reaction. And the reaction that I want to use is the one for the formation of the nickel hydroxide, or I should say nickel 2 hydroxide salt down here, this insoluble salt. As we saw in the laboratory, what we do is we add two solutions together, a solid forms, and what we have to set up is basically a double replacement reaction in the molecular equation to show the formation of that new salt. So one way to form nickel 2 hydroxide would be, say, take nickel 2 cation with nitrate. That's an aqueous solution, plus something like potassium hydroxide. That's another aqueous solution. The way I know that these two are aqueous solutions is because all nitrate salts are aqueous and all potassium salts are aqueous. Very common anion and cation to use. Sodium is also another common one. I could have used sodium hydroxide here for this reaction. When these two aqueous solutions mix together, we form a solid here. We'll get to that solid in just a second. First off, let's just sort of play the game and take a look at the double replacement reaction. And first one, I want to do these two here, okay? In some ways, this one's the easier of the two. So we have potassium, and since potassium is in that first family, we know that it takes on a +1 charge, always. Nitrate, we learned, is always that formula with a single negative charge. When these two come together in one of the products over here, they only need to come together in a 1-to-1 ratio so that they basically cancel the charges out here. Remember, when ions form ionic compounds, they come together in a ratio, the simplest ratio, so that the charges cancel out. So this is, simplest I can get is a 1-to-1 ratio. And the way that would look over here is just simply KNO3. I've already mentioned all the nitrate salts are soluble. All potassium salts are soluble. Therefore, potassium nitrate is soluble. Aqueous solution. That means there is no solid floating around in that solution. Now, let's look at the other one. This one's different. Now, one thing that's different, we already know that it forms a solid. We can see it there. Now, nickel here, nickel's a transition metal, right? It can vary in its charge state, and we have to figure out whether it's either going to be a +2 or +3. That's fairly common for a lot of the transition metals. You don't even need to remember, what are the possible charges. What you need to realize is that you can use the formula here to figure out what the charge is for a compound. Or I should say, what the charge is for a cation. As it turns out, the number of the anion here will often tell you what the charge is on the cation. So since I needed 2 of the nitrates here to balance out the charge within the nickel, that nickel means it has a +2 charge, right? Because let's just sort of break this down just a little bit, and we'll do it again here actually with the ionic formula. Trying to save a little room for that. Right, what does that 2 mean? That 2 means that there are 2 nitrates in this formula. Notice now it has a -2 charge. Why does it have a -2 charge? It's because it needs to cancel out the full-blown +2 charge on that single nickel cation. That's why there's only one nickel cation in that formula. Great. So now we know the charge on the nickel. Charge on the hydroxide? Well, it's a polyatomic ion. These are always just standard charges, has a -1 charge. Now notice, right, +2, -1, I need a ratio of 1 to 2 to cancel out the overall charge here. I need a similar thing going on with the nickel hydroxide. That's why we see that formula right down there. It's hard to see, but it's actually 2 hydroxides per 1 nickel. Because again, it needs to balance out the charge there. When you're trying to determine the molecular formula of a salt, if the charges here, if the numerical values on the charges here are not the same, 2 versus 1, then we can actually use, there's a couple expressions, I call it the flip-flop rule. The numerical value on the, like on the cation, tell me how many of the hydroxides I need. And then the numerical value on the hydroxide, 1, tells me how many of the nickel I need. And then the formula would look something like this. Just like you see right here. Right, that 2 is linked to that 2, and then the 1 there, you can imagine, right, is linked to the number of nickels. So you can switch the numerical values to figure out what the ratio is in the formula. And that's my formula that I'll put here. Okay, so now we have a double replacement reaction sitting there. And again, and try to imagine how this reaction occurred. Again, 2 aqueous solutions placed in the test tube together, a solid forms. So what we have to do here now that we know a solid form, that's our observation, we would have to decide, well, which of the 2 new products is the solid and which one's going to be the aqueous. Well, one thing you should know is that these ions here I'm about to list are always soluble. And it's sodium, potassium, ammonium are the main cations. And then for the anions, you see nitrate and acetate. Now, we can expand this list just a little bit and say that sodium and potassium are in the first family. So what that means is that, well, basically anytime you see one of these salts paired up with any other, or I should say one of these ions paired up with any other ion, it's always going to form an aqueous solution. So, I mean, that's how I know this one is aqueous. I know this one is solid because I see the precipitation reaction. I've been told that a solid forms during this reaction. The other way to do it, which actually for our class we don't have to do it this way, you can also use the solubility table to figure that out. What you find is that most hydroxide salts are insoluble with a few exceptions, and nickel is not one of those exceptions. Now the last thing that I need to do here is I need to balance the equation out. Okay, and so right when we balance an equation, we're only changing the front end of the formula there. And it doesn't really matter where you start here. I'm just going to start at the beginning here. I have 1 nickel here, 1 nickel. Don't need to do anything yet. Here I have to do something. I got 2 nitrates and only 1 nitrate on this side. So that means I need to put a 2 in front of the potassium nitrate. And then if I look at the potassium, since I've got 2 potassiums here and only 1 potassium there, I also need to put a 2 in front of that one. And then notice it also works out with a hydroxide. 2 hydroxides now on this side, and now 2 hydroxides there, and we're done. The best thing to do is focus on this reaction as a molecular equation and then worry about the ionic equation. Ionic equation is going to be very messy, very busy. There's a lot to write down here because what you're going to do is that whenever you have an aqueous salt, which 3 of the 4 here are aqueous, you actually show each individual ion in the formula and take account for the molar coefficients as well as the coefficients in the molecular formula when you're writing out how many of each of those ions are present. For example, if I interpret, right, there's a 1 in front there, 1 nickel, and there's 2 nitrates in this formula. So what I would do is something like this. Right, ionic equation, we write out the ions, taking account how many of each we have in the formula above. 2 potassium, 2 hydroxide based on the molar coefficient 2 in front. And notice I'm writing an AQ for each of these ions because they are coming from aqueous salts up here. Right? We want to indicate the phase here to tell us what we're looking at. Right? Now, once these all come together, right, the nickel and hydroxide come together to form this product. It's a solid. It stays a solid. It stays a solid here. And then just like before, since it's aqueous, I've got to break apart these ions in this notation. Now, after the first test, you don't see this anymore, okay? You don't have to write it out again in like organic chemistry or the biochemistry portion of the class. Now, this is a balanced equation. Since I use the 1 and the 2 and the 1 and the 2 in terms of factoring in the coefficients down here, it's balanced. Have all the phases in place. I have all the molar coefficients are correct. That one is done. The net ionic equation, which is actually the more common one that you see in chemistry, it's really illustrating, it's trying to highlight, how did that product form? Well, that product formed from the combination of the hydroxide and the nickel. So what we do is we take our notation here and we just pull it down into a single expression where we just have 1 nickel plus now 2 hydroxides, both aqueous tags, forming 1 nickel hydroxide molecule. And that's solid. So again, if you get the balancing and the setup correctly here on the molecular equation, you're really just using that same information over and over again to modify the notation just a little bit to deal with the ionic equation and the net ionic equation. Again, remember, the net ionic equation is trying to describe the reaction that has taken place. Last topic that's usually mentioned here is that these other ones, nitrate, potassium, nitrate. Notice they don't actually change from one side to the next. We call these the spectator ions. So in your typical, double replacement precipitation reaction, 2 of the ions will be involved in the formation of the solid. The other 2 ions will be the spectator ions for the reaction. And that's it.